Introduction to Quantum Information Processing. Welcome to Lecture 18. In this lecture, I'll begin the subject of quantum error correcting codes, which can protect quantum states from noise. I'll begin with a very brief overview of error correcting codes for classical information, and then I'll explain Shor's 9-qubit quantum error correcting code. Consider the following classical channel. Its input is a classical bit, and its output is a classical bit. It's defined relative to a parameter epsilon, which is between 0 and 1. If the input bit is b, then the output bit is b with probability 1 minus epsilon, and the logical negation of b with probability epsilon. In other words, the channel flips the bit with probability epsilon. This channel is called the binary symmetric channel, and we abbreviate it by BSC, sometimes with a subscript, to specify the parameter epsilon. This channel can be viewed as a classical analog of the depolarizing channel. Remember the depolarizing channel that takes a qubit as input and produces as output a probabilistic mixture of that state and the maximally mixed state? The binary symmetric channel outputs the input bit with probability 1 minus 2 epsilon and the classical maximally mixed state with probability 2 epsilon. The classical maximally mixed state is a uniformly distributed random bit. Now suppose that Alice wants to communicate a bit to Bob, and their communication channel is a binary symmetric channel. That is, it flips the bit with probability epsilon. So, with probability epsilon, Bob receives the wrong bit. So how can Alice and Bob reduce the noise level to a smaller epsilon? The obvious way is for Alice and Bob to get a better communication channel. But Alice and Bob have an alternative to investing in better hardware. They can use an error-correcting code. Perhaps the simplest error-correcting code is the 3-bit repetition code, which works as follows. To transmit a bit B, Alice encodes B into 3 copies of B. Then Alice sends each of these 3 bits through the channel. Then Bob receives 3 bits at his end, but the 3 bits are not necessarily the same. Some of the bits may get flipped by the channel. Bob decodes by taking the majority value of the 3 bits that he receives. How well does this perform? The system succeeds if no more than 1 bit is flipped, because that doesn't change the majority, and it fails if 2 or more bits are flipped. Assume that the channel behaves independently for each bit that passes through it. Then the failure probability can be calculated as follows. There are 3 ways that 1 bit can be flipped, each occurring with probability epsilon squared 1 minus epsilon. And there is 1 way that all 3 bits can flip, occurring with probability epsilon cubed. This simplifies to 3 epsilon squared minus 2 epsilon cubed. Here's a plot of this as a function of epsilon. If epsilon is 1/2, then there is no improvement. The success probability remains at 1/2. But this should not be surprising, because if epsilon is 1/2, then the channel sends no information. It just outputs a random bit uncorrelated with the input bit. But when epsilon is smaller, there is an advantage. For example, when epsilon is 1/10, then the failure probability from using the code reduces from 1/10 to about 1/35. And if epsilon is smaller to begin with, then the reduction becomes more pronounced. For example, if epsilon is 1 over 1,000, then the failure probability from using the code is 1 over 300,000, a 300-fold decrease. What price are we paying for this improvement? The main cost is that 3 bits have to be sent instead of 1. The rate of a code is the inverse of the message expansion. The rate of this code is 1/3. Each bit of the encoding conveys 1/3 of a bit of the data to be transmitted. If the data is a long string of bits, then there will be some errors, but fewer errors using the code. With no code, the fraction of errors is epsilon. With the code, the fraction of errors is 3 epsilon squared minus 2 epsilon cubed. Suppose that Alice wants to send a gigabyte to Bob. That's around 8.5 billion bits. And suppose their communication channel has parameter epsilon is 1 over 100. Without the code, the fraction of errors will be about 85 million. With the code, the fraction of errors will be about 24,000. That's significantly fewer errors, achieved at the cost of sending 3 gigabytes instead of 1. But suppose that we don't want any errors. Can this be achieved? One approach is to use a larger repetition code than 3 bits. That reduces the error probability for each bit, but this also reduces the rate, so many more gigabytes would have to be sent. But there are much better error-correcting codes than this. In fact, there's this amazing result about multi-bit codes. For any binary symmetric channel with any parameter epsilon that's strictly less than 1/2, the success probability of the whole string can be made arbitrarily close to 1 while maintaining a constant rate. So in fact, Alice doesn't have to send many gigabytes in order to get every single bit through to Bob correctly. To state this result more precisely, let's begin with some basic definitions. Assume that blocks of n are encoded into blocks of size m, and there's a decoding function that goes the other way. Note that the rate of the code is n over m. The smaller the rate, the more bits that have to be sent. For any m-bit encoding, the channel BSC epsilon randomly flips each of its bits with probability epsilon. To communicate a string A, Alice applies the encoding function to produce an m-bit string. Then Alice sends those bits through the noisy channel where some of the bits might get flipped. Bob receives the perturbed encoding at his end and decodes it to produce an n-bit string that I'll call A prime. The error probability is the probability that A and A prime differ in at least 1 bit position. To succeed, every single bit of A has to be recovered by Bob. Next, I'm going to state the result about what good error-correcting codes can achieve. Please note that I'm not going to give the details of the construction or the analysis. The theory of error-correcting codes is a large field of study that could easily take a course of its own to explain. Suppose that the error model is a binary symmetric channel with parameter epsilon for each bit. What's the best rate possible? The Shannon entropy of of the probability vector epsilon 1 minus epsilon is defined as this expression. Define R of epsilon as 1 minus the Shannon entropy. Here is a plot of this function. I'm now going to state the result about good multi-bit error correcting codes. Let the noise level be any epsilon less than 1/2. Think of that as a property of the communication channel that you're stuck with using. Then you can select any rate R as long as it's less than R of epsilon, as long as it's below the curve. And you can select an arbitrarily small positive number delta, which is your desired error probability bound. Then there exists an error correcting code whose rate is at least R and whose success probability is at least 1 minus delta. Just to be clear, success means all the bits are successfully transmitted, that there are no errors. There are additional considerations that I'd like to mention, even though I won't go into the details. One is the block length n. The smaller delta is, the larger n has to be. Another is the computational cost of computing E and D. The bottom line is that there are codes for which this can be done efficiently. Okay, so that was a very brief overview of error correcting codes for classical information. The question is, what happens with quantum error correcting codes? We started with a simple classical error correcting code, the 3-bit repetition code. Is there a quantum repetition code? How would that work? Well, we could try encoding a qubit by making 3 copies of it. And then we could decode by taking the majority value of the 3 bits received at the other end. How does that sound? Anything wrong with this? Well, for starters, we cannot make copies of a qubit due to the no-cloning theorem. And it's not even clear how we take the majority of 3 qubits. So this definitely does not work. It's easy to copy classical information, and all error-correcting codes for classical information are based on some sort of redundancy. But the no-cloning theorem kind of suggests that redundancy might not be possible for quantum information. That was the thinking shortly after Shor's algorithms for factoring in discrete log came out. Maybe large-scale quantum computers cannot be built because of the problem of resiliency against noise. Many people thought intuitively that it might be fundamentally impossible to overcome this because of the no-cloning theorem. But this intuition was wrong. In the remainder of this lecture, I'm going to show you the first error-correcting code that was discovered by Peter Shor in the mid-1990s. Let's start with a simple 3-qubit code that protects against a very restricted error set. Suppose that the only error possible is a poly X, a bit flip. Then these encoding and decoding circuits protect against up to 1 X error. The encoding circuit takes a qubit as input and produces 3 qubits as output. Then an error operation that can be one of these 4 can occur. No error, an X applied to the first qubit, an X applied to the second qubit, or an X applied to the third qubit. Then the 3 qubits are input to the decoding circuit. It turns out that in all 4 cases, the final state of the first qubit will be the same as the initial state of the first qubit. It's a straightforward exercise to verify these, but I recommend that you work through at least some of these cases to convince yourself. If you work out the final states, you will see that the second and third qubits end up with different values depending on what the error operation is. We'll refer to these 2 qubits as the syndrome of the error. Not only do the encoding and decoding protect the first qubit against the errors, but the decoding process also reveals what the error was. Okay, that's all fine for X errors, but what about other errors? Specifically, what happens if there is a Z error? That is, a Z applied to one of the 3 qubits in transmission. Please pause if you'd like to think about this. A Z error is not corrected. Instead, it's passed through. By this I mean that it's equivalent to applying a Z to the original data, which has the effect of negating the sign of the amplitude alpha 1. Now, here's another 3-qubit code protecting against only Z errors. This code is essentially the same as the previous code for protecting against X errors, but with a layer of Hadamard gates added to the end of the encoding and the beginning of the decoding. What the Hadamards do is convert Z errors into X errors. Think of a Z error and the Hadamard gates. Since HZH equals X, they become X errors, and then they are handled as the previous code does. So this is essentially a repurposing of our code for X errors to protect against the Z errors instead. Okay, so we can protect against just X errors or against just Z errors. What if we want to protect against any 1-qubit unitary as an error? This is accomplished by the following 9-qubit code. In this code, there is an inner part consisting of 3 blocks, where each block is a copy of our code for X errors, and there is an outer part which is our code for Z errors. What happens if there is an X error? It is corrected by the inner part. What happens if there is a Z error? A Z error passes through the inner part, and then the outer part corrects it. What happens if there is a Y error? Since Y equals IXZ, and the phase I makes no difference in this context, this can be viewed as a Z error and an X error. The inner part corrects the X error, and the outer part corrects the Z error. So if there is any poly error in 1-qubit position, then it is corrected by this code, and the final state of the first qubit is preserved. The final state of the 8 qubits following the first qubit is called the error syndrome and contains information about which error was corrected. What happens if there is an error in 1 qubit which is a unitary operation other than X, Y, or Z? Any 1-qubit unitary U is expressible as a linear combination of I and the 3 polys, and we can work out the final state of this error-correcting code. The final qubit ends up in the correct state, and the syndrome ends up in a linear combination of the syndromes for I, X, Y, and Z in that position. I will leave it to you as an exercise to confirm this. It's an easy exercise based on the linearity of all the operations. Our discussion of classical error correcting codes was based on the binary symmetric channel, for which any bit that passes through it flips with probability epsilon. Here's a quantum analog of that channel. A qubit can be flipped in more than one way. An X error is a bit flip. A Z error is a phase flip. And a Y error is like flipping the bit and the phase. This channel leaves the state alone with probability 1 minus epsilon, and with probability epsilon does one of the three flips, each with equal probability. We've actually seen this channel before, but in a different form. Do you recognize it? This is actually another way of describing the depolarizing channel that maps each state to a convex combination of that state and the maximally mixed state. In other words, it shrinks the Bloch sphere towards the center. How do we know that the two channels are the same? I'm leaving this as an exercise to check. It's not entirely trivial, and I recommend that you work this out. You might start with any pure state for your qubit and calculate the density matrix of the state that the channel on the left produces. You'll see that it is equivalent to the channel on the right. What's the value of p as a function of epsilon? Let me give you a hint. P is not equal to 1 minus epsilon. This new way of looking at the depolarizing channel is nice. It's clear that with probability 1 minus epsilon, the state that passes through it is not disturbed, and otherwise the state undergoes some sort of Pauli error. If Alice wants to communicate a qubit to Bob through a channel that is depolarizing with parameter epsilon, then if they use the 9-qubit code, the effective error probability becomes a constant times epsilon squared. I don't know the exact multiplicative constant. I haven't worked it out, but it's less than 36. So if epsilon is small enough to begin with, then the effect of squaring epsilon is more pronounced than the effect of multiplying epsilon by c, so the effective error is decreased. The cost is that Alice has to send 9 qubits to convey just 1 qubit, so the rate of this code is 1/9. Are there good multi-qubit error-correcting codes for quantum information? I will discuss this in the next lecture. Before concluding, I'd like to step back and look at what has been accomplished. Our code encodes a qubit into 9 qubits, and this is the state of the encoding. It is a superposition of what's called a logical 0 and a logical 1 state. The encoded state has the property that if any error is inflicted on any one of its qubits, then the data can still be recovered. To be clear, note that the recovery procedure is not provided with any information about which qubit has been affected by an error. So which of the 9 qubits contains the data? The answer is that no individual qubit contains any information about the data. This information is somehow spread out among the 9 qubits in a manner that makes it robust against a 1-qubit error. There are not multiple copies of the data embedded in the encoding. The natural question is whether there is a more efficient code that requires fewer than 9 qubits and protects against any 1-qubit error. This question will be answered in the next lecture. Finally, I'd like to explain a different type of error called an erasure error. For this type of error, the positions of the affected qubits are known. One way of viewing this is that some of the qubits are lost, but we know the positions of the lost qubits, and the remaining qubits are undisturbed. For example, suppose that we have our 9-qubit encoding, except we're missing qubits 2 and 6, as illustrated. It turns out that this type of error is easier to correct because we know the positions of the errant qubits. The Shor 9-qubit code can handle any 2 erasure errors. From any 7 of the 9 qubits, the data can be recovered. Finally, here's a theorem that's easy to prove, but it helps clarify the distinction between redundancy and copying. There cannot exist a 4-qubit code that corrects against 2 erasure errors. Why not? Suppose that we had such a code. Then take the first 2 qubits and think of them as an encoding with 2 missing qubits. Same with the last 2 qubits. If the code could really protect against 2 erasure errors, then we could recover the data from each of these, thereby producing 2 copies of the data, and this would contradict the no cloning theorem. The 9-qubit code does not contradict the no cloning theorem, because if you take 7 qubits to recover the data, then the 2 qubits that remain are not enough information to recover a second copy of the data. In fact, any 2 qubits will contain absolutely no information about the data in that code. Okay, let's end the lecture now.